Good morning, everybody. Glad to have you all here. Just a quick heads up, we're going to start in about 5 minutes because we're still waiting for some participants to join. So yeah, just bear with us. We'll be beginning shortly. All right. Well, it seems that we got most of most of us here, and I suppose we can begin. Right. So first off, some basic items to mention. If any of you wish to receive a certificate of attendance for this webinar, you can get one from Globecore. You can ask for it in the chat window here in Zoom, or you can contact the Globecore managers who actually invited you to this webinar. They'll set up the certificate for you. Also, I'm sure there will be questions during the webinar, and rather than interrupt the presentation to answer those, please ask your questions in the chat window in Zoom and or in YouTube, for that matter, for those of you who are watching this on YouTube. And somebody will get back to you. No question will be left unanswered. Some questions will be answered during the presentation, and this is usually the case. And if we run out of time and some questions are left over, then somebody will get back to you with those answers. So, okay, with this out of the way, once again, welcome to this webinar. Glad to have you all here. My name is Anton. I'll be the presenter on behalf of Globecore today. And our topic of interest today is moisture and hydrogen in transformers. These two things are always bad. They indicate there is some degradation process going on. Moisture can be the result of destruction of oil or vapor, or it may come from the environment if there is a leak in the transformer. And hydrogen is a gas that always forms when there is an electrical or thermal fault in the transformer. So the correct measurement and management of these parameters is absolutely critical to extend the service life of that transformer unit. Next slide, please. First thing we want to I'd like to address is how moisture and hydrogen form in the transformer. So let's begin with the beginning here. Next slide, please. So when we talk about moisture, the first thing we have to determine is where it comes from. In transformers, there's a few ways that moisture can form. There are different ways in which transformer can generate its own moisture. In some cases, we can sometimes limit or reduce that by our actions. And some processes will occur regardless of what we do. So the process of increasing the moisture inside the transformer is very dynamic. And among the main reasons for the increase in humidity inside the transformer, we can name some of the following. There is residual moisture left over from the manufacturing process. Although factories and manufacturers do strive to reduce the moisture content, not all factories are equal, and some do less than others, and in some products the residual moisture content is going to be higher. And there are factories that do not prepare oil before filling, or even factories that don't have a system for drying transformer windings, and that would give us relatively high levels of moisture in the transformer from the start. Moisture can ingress into the transformer during poorly done repairs. There are processes in which there is an impact on the transformer windings from the environment. So the transformer repair company must implement systems that prevent moisture from the environment from being absorbed in the windings or oil. In addition, a shop or a factory must be equipped with certain oil treatment systems, and we'll address those a little later. Since any sort of negligence in these things can increase the humidity of the transformer, and that creates big problems in the future down the line. One way of contaminating transformer with moisture is through leaks, because this happens when there is an opening or leak in the transformer, and we can see the moisture come into the transformer when there is an oil leak. Transformer is a breathing machine, so when the load increases, the temperature also increases, and this pushes out the air from, this causes the metals to expand, and at this point we will see oil coming out of the transformer. But when the transformer cools down and the metals cools down, and this will cause compression and negative pressure, and the gases from the environment will be sucked into the transformer, and they will contain moisture and other things we don't want in the transformer. And water also comes from inside the equipment because aging oil and insulating paper contribute to the formation of moisture in a similar manner. Next slide, please. During oxidation of oil, water is actually formed as a byproduct. So in this case, you can call it probably an advantage. Oil has a high solubility, so we don't get free water. But oils with high moisture content can foam very much during degassing, and that can be a problem. It's always recommended to process oil to achieve low moisture content before filling the transformer, because the paper insulation system has a very high affinity for water, and it will absorb water very eagerly. The greatest amount of moisture in transformer is always in the paper, and this water, it causes decomposition of the paper's fibers and causes irreversible damage that can lead to electrical discharges in the transformer. And when the oil is heated, the total water content does not decrease. It only increases solubility of water in the oil, so some of the water goes out of the paper and into the oil. But in any case, any changes due to temperature will only transfer water inside the transformer from paper to the oil and back again. So there's not going to be free water, but the total amount of water in the transformer remains the same. Next slide, please. Okay, the formation of hydrogen in transformers occurs as a result of destruction of oil molecules. We know that transformer oil is a hydrocarbon. It's basically a long chain of carbon and hydrogen atoms, hence the name. And when energy rises, which can be caused by electric current or by high temperature, atoms can break off of that chain. So we will have free atoms in the insulating liquid. These atoms have certain energy, and this will allow them to rearrange themselves into different compounds. For example, for hydrogen, two hydrogen atoms stick together, and then there you have it, some hydrogen. This process also generates other gases depending on the amount of energy. These can be methane, ethane, ethylene, acetylene, and others. And this rearrangement is one that we use extensively for diagnostics, for gas chromatography, and for and statistical studies of this process have allowed us to find out malfunctions which are associated with formation of various gases. There are two processes of gas emission in the transformer. If the gas produced contains hydrogen and hydrocarbons, this indicates the breaking of the carbon-hydrogen bonds of the oil by electrical discharges, and this process is known as gasification. If the released gas does not contain decomposition products, then this process is known as dissolved gas emission. And both forms of gas emission are very important in high voltage electrical equipment. Next slide, please. But the formation of hydrogen in transformers occurs as a result of the production of hydrogen transformers is normal. With thermal or electrical problems, we can pretty much guarantee that hydrogen will be generated in any case for all of the faults that occur in the transformer. So this will be very common as we find larger quantities of this combustible gas in our transformers if we have some thermal or electrical fault. If the gas is produced in large quantities, the resulting bubbles actually pose a hazard to the transformers, as they can cause electric discharges due to the poor insulating properties of the gas as compared to the oil. Hydrogen is usually associated with low intensity problems, but as you can see in this graph above, hydrogen is generated in all faults, all kinds of problems. And when studying faults of greater intensity, the characteristics, we use characteristics of gases for the formation. We use gases for which a lot more energy is required, but we will still always register continuous increase and buildup of hydrogen. And this is why there is a series of sensors that only monitor hydrogen level. This allows us to know if there is a change in the operation of the transformer. It's also usually a gas with one of the highest concentrations in chromatographic studies. So knowing the amount of hydrogen in oil is a very good indicator that allows us to determine the state of thermal vacuum processes and degassing processes as well for the oil. Next slide, please. Next, I'd like to talk briefly about the limits and what we should look for when we process our oil and maintain our transformers. Next, please. So water in the transformer is one of the elements that we really need to keep track of and monitor. However, it's one of the most difficult characteristics to control. There are several processes by which transformer generates moisture, and there are various parameters that will all be related to moisture, and they will affect all our attempts to keep the transformer dry. For example, our actions will always focus on reducing the amount of moisture in parts of equipment, which refers to the amount of moisture found free in the transformer. But there are other ways to determine moisture. For example, moisture present in paper and moisture dissolved in transformer oil. If we want to have a dry transformer, we must make sure that moisture does not form or is not contained in any of these three forms. And one of the most difficult to deal with is emulsified water, for instance. The various states of moisture inside the transformer are interrelated with each other, and they're not static because water can move and change from one state to another because water from the paper, when temperature increases, water from the paper will be carried out into transformer oil because of the increased solubility. On the other hand, water contained in the oil can also go back into the paper because this, again, varies with solubility, varies with temperature. For this reason, it's recommended to always try and maintain a very low moisture level in transformer, which allows to extend the service life of the unit. And we must remember that water inside the transformer behaves like a catalyst because it promotes actual harmful chemical processes. With water, they flow faster and easier, and that greatly affects the service life of the unit. We know that oxidation processes occur much faster in the presence of water, and we know that paper is seriously affected when moisture is present inside the transformer. And these are just the two possible problems that can arise in our units when the humidity rises. So this is why it's very important to know the current moisture levels present inside the transformer in different forms, and also to take steps to correct that. It's important that during these adjustment processes, an adequate moisture measurement is made so that we can optimize any dehydration process that we run to know that this process is in fact effective. Next slide, please. The amount of moisture in ppm in transformer oil varies, the limiting amount, depending on the type of fluid, excuse me. For example, for the IEEE C57-106 2015 standard, there are specific values for mineral oil. The amount of moisture in a transformer depends on when it's measured. So we see that new oil has relatively low permissible values, whereas for transformers below 69 kilovolts, here we have a value of 20 ppm, and for transformers above that, we need 10 ppm. For transformers that have been in use, they're in continuous use, the values differ, and we'll see that we have 35 ppm values for 69 kilovolt transformers, and as opposed to 25 for 69 to 30 kilovolt transformers, and just 20 ppm for transformers over 230 kilovolts. And in this case, the suggested values are presented for reconditioned or reclaimed mineral oil in transformers, and we see that for such insulating liquid, the voltage level at which they operate is important. For example, for transformers smaller or less than equal to 69 kilovolts, the value is 35 ppm. In transformers from 69 to 230 kilovolts, we have an amount of 20 ppm. And for anything larger than 230 kilovolts, the acceptable value is just 15 ppm, although it does, the standard does say that it's better to have something closer to 10 ppm or less, if possible, for reconditioned oil. For example, in silicone oil, these values will be different, and the permissible ppm will be 50 ppm. And transformers with natural oils, which are known for their high resistance to water, the values will be from 300 ppm to 100 ppm, depending on the voltages at which the transformer operates, with 300 ppm for smaller transformers below 69 kilovolts and a maximum of 100 ppm for transformers over 230 kilovolts. So moisture ppm is just one parameter. We also have to control the saturation, the relative saturation of oil with water, and the amount of water that is transformed from oil to paper. And these are two important constraints that we must take into consideration. Next, please. Need the next slide, please. Thank you. So standards define the acceptable moisture saturation values for mineral oils. As you can see, these values also depend on the operating voltage of the transformer. If for transformers less than 69 kilovolts, it's considered acceptable. If the saturation value is less than 15, it becomes problematic, questionable if this value is between 15 and 20%. And anything higher than 20% is unacceptable. Now, if we look at the bottom line of the table, we'll notice that for transformers above 230 kilovolts, the saturation values are quite a bit more stringent. For transformers with voltages over 230 kilovolt, the allowable value is less than 5% saturation. So from 5 to 7% is problematic, and anything over 7% is unacceptable. Saturation has a serious effect on breakdown voltage, especially if tested in accordance with the ASTM D1816 standard. Next slide. Another important thing to consider when determining moisture, I'm talking about moisture in the transformer, is the amount of moisture transferred from oil into paper. There are various parameters that are used to determine this amount of moisture. Most of them state that a value greater than 2% means that transformer is wet. So we can see that IEEE 62 defines three values that are subdivided as follows. Transformers with a percentage of less than 2 are considered dry. Anything higher than 4% is considered excessively humid, and transformers that are between 2 and 4% are extremely wet transformers. So it's recommended to perform dewatering processes on those transformers to extend their lifetime. There are also other standards that add other values to this scale. For example, the SIGRAE standard, which defines the value for new transformers, i.e. all those that are equal to or below 1% saturation would be a good new transformer. While IEC 6422 defines moderately wet, and extremely wet values, where 3.5 to 2% transformer are considered moderately wet transformers, values above that range are considered extremely humid. High moisture levels in transformers are obviously undesirable, since paper is continuously being destroyed if there is water, and it's a very possible danger that a transformer may just stop, leading to a critical failure. And these failures are such that the transformer sometimes might not even be able to be repaired without serious effort. And in some cases, it just cannot be repaired entirely and must be written off. Next slide, please. The permissible amounts of gases in the transformer depend on various parameters. The first thing that we need to consider is the relationship between oxygen and nitrogen. As we can see in this table, this gives us two large groups. On the one hand, we have transformers with this ratio of less than or equal to 0.2. The other large group includes transformers in which this value is greater than 0.2. And it makes it necessary to know other parameters in order to determine the acceptable limits. We can also observe how age of the unit is important in determining the allowable values for the content of hydrogen and other gases. We have here four clearly differentiated groups, where we have a value for those transformers whose age is unknown, a different value for transformers between 1 and 9 years old, and another value for transformers between 10 and 30 years old. And finally, there is a specific value for units over 30 years old. Obviously, the values have a lot of variation. For example, for transformers, the ratio of oxygen to nitrogen is greater than 0.2, then the maximum allowable values are 40 ppm. And with a ratio less than or equal to 0.2, there are three different acceptable values. For transformers whose age is unknown, we can have an acceptable maximum limit of 80 ppm. For transformers from 1 to 30 years old, the maximum value will be 75 ppm, and transformers over 30 years old will actually allow us 100 ppm. So this mechanic must be repeated for all gases the transformers are tested for, and the permissible amount of gases in the transformers must be below any of the values indicated in this table in this line. Next slide, please. The unacceptable amount of hydrogen is determined in much the same way as the allowable amount of hydrogen. So we're going to take into account the same parameters with which we will start the analysis with the oxygen-nitrogen ratio. And we determine which section of the table we work with. So then we determine the number of years, the age of the equipment, and then we're going to determine the limits of the hydrogen content. Any value exceeding these limits is going to be considered acceptable. So we can see that hydrogen values that are considered acceptable vary greatly. In transformers with the oxygen to nitrogen ratio above 0.2, we should not have values higher than 90 ppm in any case. While for transformers with ratios of oxygen to nitrogen less than or equal to 0.2, that range is much wider, about 200 ppm, regardless of the age of the unit. Now, if we recall the previous table, we will see that there is a range of values that are considered to be warning ranges, because if the hydrogen value exceeds the values from the previous table, but does not exceed the values in this table, we can determine that the transformer is in a questionable state, and then it means that we need to conduct a deeper investigation into the possible fault or malfunction, and where we can also take into account the values from other tests that we can and probably should perform, which is of great interest and will be very good for determining the exact possible fault and determine and identify the subsequent repair and reclamation process. It's important to clarify that when we have a problem associated with the formation of gases, we first tackle and address the element that generates the indicated gas, and only then we proceed to perform a degassing process. Because if we don't take corrective measures and just do the degassing, then very soon the oil will just have the same gas again. Next slide, please. Whenever studying transformers, the most important parameter is the rate of change, actually. It's not so much the flat number, but the rate at which that number changes. So whenever we have an abrupt change, it's important to be able to determine what is causing that change. And it doesn't matter if the change is still within acceptable values. Any sudden inappropriate changes identify incipient problems in the transformer. The C57.104/2019 standard defines the values of the allowable rate of change between successive laboratory analysis. This rate of change does not take into account the age of the transformers, but does take into account the ratio between oxygen and nitrogen. And again, gives us two large sections in the table for where the values are less than or equal to 0.2. Here we have a rate of change of no more than 40 ppm possible, but when the ratio is over 0.2, no more than 25 ppm change is allowed. It's important to note that these changes are not directly related to the previous tables, because if the changes presented in this table take place regardless of the status based on oil levels, the transformer will be determined as a status 3 transformer. Next slide, please. So to look a little deeper into the problems that can be caused by the moisture and hydrogen in transformers. Next slide, please. Okay, so moisture saturation affects many parameters of the oil, such as power factor, interfacial tension, and the breakdown voltage, but it's especially important for the breakdown voltage. We can see some big changes here. This in this curve here, and it's developed by the company Vaisala. They used online measuring equipment that allows to know and record specific changes that occur in oil. So they were able to determine and plot this curve for the breakdown voltage as a function of the relative humidity of the oil. And we can see that at low moisture and saturation values, we have rather good values in terms of RV in that oil. But when saturation begins to increase, we can see a significant decrease in this parameter, a condition that is especially critical for high voltage transformers, because one of the components, if one of the components of the insulation system loses its dielectric characteristics, we can see that basically the saturation increases at levels above 40%, we lose 70% of the insulating properties. So as we mentioned earlier, saturation greater than 5% is not recommended for transformers with voltages above 230 kilovolts. So knowing the moisture saturation in our oil is critical for both the recovery process and for continuous operation of the transformer. Next slide, please. Moisture saturation is that ratio that links the amount of dissolved moisture to the amount of moisture that can theoretically be dissolved. So this value is usually expressed as a percentage. This means that 50% saturated oil basically uses up half of its water dissolution capacity. Of course, the actual numbers of water content are small, so we're talking about something like differences of parts per million. So this characteristic is seriously affected by temperature. And for this reason, it's very important to know the temperature of the sample that we take at the time of sampling, or at least to have equipment that can provide these values. An example of moisture saturation looks like this. An oil with a temperature of 40 degrees has the ability to hold, for example, 120 ppm of water. So if the oil contains 24 ppm, the temperature of this oil is 40%, 40 degrees, the relative saturation will be about 20%. And in this case, if the oil had a concentration of 60 ppm, that would mean that the saturation is 50%. Next slide, please. So as we mentioned earlier, temperature is the parameter that probably most seriously affects the moisture saturation of the oil. And in this graph, you can see the effects of temperature rise on 4 different oil types. We can observe how mineral oil works at temperatures below 30 centigrade. The water absorption capacity is less than 100 ppm, but when the oil is any close somewhere around 100 C, this temperature rises. The saturation rises to about 900 ppm. So the effect on silicone oils, lubricating oils, and vegetable oils changes as well. It changes the proportions of moisture that these fluids can absorb. Another element to consider is that as the temperature drops, this dissolved water will actually separate from the oil and become free water. And this can cause big problems if the amount of water released from the oil is large enough. Or this water can migrate and probably will migrate into the paper insulation because, being free droplets, it will move around inside the transformer. And one of the characteristics of paper is its affinity for water, which increases the percentage of moisture that will be present in the solid insulation. So the only way to keep moisture saturation low is to keep the humidity of the entire system low, not just the oil or the paper, because if we have high saturation, it will permeate and damage all elements of the transformer. Next slide, please. Okay, Martin Engelhuber defined water as a slow but deadly poison for transformers, and I couldn't agree more. This is 100% true. Water reduces the breakdown voltage, which allows electric arcs to exist inside the unit at a lower voltage. It accelerates the decomposition of paper, which directly reduces the lifetime of the transformer. And we must remember that the life of the transformer is always measured according to the durability of its paper and its ability to withstand the electrical and mechanical stresses. Water causes oil aging. As we said, water is a catalyst, and it accelerates all chemical processes that can occur inside the transformer, including oxidation of oil and destruction of paper. Water reduces the mechanical strength, physical strength of paper insulation. We all know that, how paper reacts to moisture. Its mechanical strength is basically destroyed. So any water in paper is bad. So the same situation occurs inside the transformer. Wet paper is not a good, strong material. Water reduces the electrical resistance of not only oil, but of the entire insulation system, which causes deterioration in all performance characteristics of insulation. We can see this in this graph above provided by Sintef. It examines the effects of temperature in combination with water on solid insulation, and it shows the expected life of kraft paper on the blue line here, the top line. We can see the expected life of the paper when it's completely dry. It's clear that as temperature rises, the useful life is reduced. And now we can see down below is a purple dotted line, and we can see the effect of 1% of moisture in the paper, which when operated at 80 degrees centigrade can have an approximate life of about 30 years. And 30 years is not bad. It's an acceptable good value for a transformer, but We see that with an increase of just 3% to 3%, and with operation at 80 degrees centigrade, we can see the service life is just 6 years now. So we just lost 24 years of operation with an increase of moisture content of the paper just 2%. So this graph is a very good illustration of the importance of keeping the moisture content in the transformer as low as possible at all times. Next slide, please. So what has been said above can be easily summarized in these two little tables. Increasing moisture in paper will decrease the expected life of paper by up to 60%. So for thermally enhanced paper, this reduction is a bit smaller, but still it's very important because it's nearly 35% less than the expected life. So with these numbers, we can easily understand just how important moisture and moisture removal is for transformers and insulating fluids as well. Okay, next slide. Now we've talked about moisture a lot. Let's go back to hydrogen. So the presence of hydrogen is usually associated with things like partial discharges, corona effects, and hydrolysis. Hydrolysis is the same process where water is formed. As we've seen, the processes of internal water formation that we discussed, these are very similar. The corona effect is an electrical discharge that occurs due to ionization of gas that surrounds conductors, where the potential gradient exceeds a certain threshold. This effect is usually observed on power lines with voltages around 30 kilovolts per centimeter. Partial discharges are incomplete electrical arcs or discharges, and all of these are large generators of hydrogen. These are some typical transformer problems that need to be addressed whenever we see them in order to increase the service life of the transformer units. Next slide, please. So now let's talk about some of the methods that we can use to measure the amounts of water and hydrogen in transformers. Next slide. So to solve the problem, we first need to quantify it. So in our case, this means measuring the amount of water in the oil and in the transformer in general. And there are several ways to do this. We have capacitive sensors. We have some clever laboratory methods, such as Carl Fisher. We can do field measurements, such as dew point. And there are some electrical techniques, such as frequency domain spectroscopy. And each of these methods may be convenient in a given situation, and there will be some methods that may be more reliable than others, but the goal is to always have reliable equipment to make precise measurements and to know the problem entirely. Next slide, please. Right, so the Carl Fisher is a titration method for quantifying the water content of liquids and solids. It's one of the most commonly used measurement methods today. A sample is dissolved or suspended in a suitable solvent free of water, which would usually be dry methanol. And an iodine reagent is added with an automatic portioning device. So the water in the sample reacts with that chemical until it's completely consumed, and so free iodine is found in that solution. The endpoint of the titration is determined voltammetrically with a platinum electrode. And Carl Fisher titration is used in many fields, such as determining the water content in foods, chemicals, drugs, cosmetics, and mineral oils as well, of course. And this water content affects the physical and chemical properties of products that can be related to their freshness or shelf stability. But in the oil industry, water is one of the largest contaminants. However, in cosmetics, for example, it's one of the main components. So the control of exact amount of water is necessary to preserve the properties of products in either case. Next slide, please. A capacitance sensor, it's a method for measuring humidity. Basically, an electrical property of the sensor membrane changes depending on the moisture present. The membrane exchanges moisture with the dielectric oil, and it changes the membrane's capacitance. And that is recorded and converted into a moisture reading. And these sensors are quite typical for field processes, and those sensors are optionally available for moisture control with all globe core equipment. Next slide, please. So the dew point of a gas, the dew point method, Right. Okay. We're good to go, I hope. So the dew point of a gas is, by definition, the temperature at which the moisture begins to condense on the surface that is in contact with gas. And based on this value, the total amount of water it contains, as well as its relative humidity, can be figured out from a known volume. The amount of water in paper is determined as a function of the relative humidity of the gas with which it contacts when it's exposed until there is a certain equilibrium condition between the respective moisture levels. At present, there is enough experience to safely say that this method for determining moisture content is correct and possesses sufficient accuracy. The general procedure usually is to fill the transformer with dry gas, that would be air or nitrogen, in such a way that after a certain time, during which a state of equilibrium in humidity is achieved, the dew point of gas is then measured, and that value allows us to determine the residual moisture in the solid insulation. Next slide, please. So the dew point is converted into vapor pressure using these graphs. The temperature of the windings is measured, preferably using ohmic resistance. Or we can measure the temperature of the gas, because after 24 hours in the transformer, it's likely that the gas is the same temperature as the windings. So from this measured value of the dew point and the pressure of the gas, air or nitrogen inside the transformer, the vapor pressure is determined. And from the vapor pressure and the temperature of the windings or gas, we can figure out the residual moisture according to this graph, which is also known as the Piper plot. Next slide, please. So the results of the analysis here show that the real dielectric constant and the imaginary dielectric constant, virtual, I guess, dielectric constant, increase with the decrease in degree of polymerization at the low frequency stage, while they remain unchanged at the high frequency stage. Increasing the moisture content of the oil impregnated paper would increase the actual dielectric constant to 102 Hertz and the apparent dielectric constant throughout the frequency test. The curve of the imaginary part, together with the increase in water content, will show a trend shifting towards the right. Next slide, please. So the decision to perform oil purification and drying requires information on the current condition of the oil at the transformer. And besides, it's important to keep track of how efficient those processes can be or are. The methods that we spoke about above are to an extent indirect, and this is why Globecore is currently making the Tor product line available to our customers. This product line is designed to support oil recovery and regeneration in the field, but it's also perfectly suitable for use in any laboratory. The Tor 1 is a device capable of measuring the amount of moisture present in the oil and also measure its temperature. The important part here is not that the parts per million measurement, but the indication of the activity of water in the oil. And this device is rather small and compact. It's pretty easy to handle and carry around if need be. And you could just watch a quick video here on this pretty little thing. Next slide, please. Can we go to the next slide now? Thank you. So basically, yeah, once again, it's a device that measures the active water in the oil with a capacitive sensor. And the sensor is such that it gives us very good long-term stability. It has a pretty good resistance to any contaminants, measures the active water and the temperature of the sample. And using these values, there is an algorithm that allows the calculation of actual moisture content in parts per million in the mineral oil. Once again, the device can also be used for other types of oil. It is not limited only to mineral transformer oil. Next slide, please. So one of the main advantages of the Tor line is the simplicity. It really has the parameters that allow easy read and measurement of humidity in the field. This is a device designed specifically to be lightweight and easy to handle and carry around. Water activity is measured on a range from 0 to 1. This is a parameter that determines how much moisture the oil has absorbed. So it allows the system to give us a reading from 0 to 500 ppm with a very good accuracy. It also measures the temperature. So this is all done very quickly. The device is, again, very good for field work. With a weight of just under 6 kilograms, it's pretty easy to handle, but it can also be used as any laboratory setup with no problem at all. Next slide, please. In addition to to our usual filtration regeneration equipment for oil, we got this TOR2 instrument, which is designed to measure the hydrogen content in the oil, as well as moisture and temperature of the oil. A standard lab test would likely take at least 1 day. So that's a waste of time and resources, increases the cost of services. So this little product by Globecore allows the client, or the operator rather, to perform these tests independently. This device was developed to give accurate readings that will characterize the degassing and dehydration processes, and will reduce the time of work in the field and allow the operator to safely diagnose the ongoing process with a good degree of precision. Some of the important features of the TOR2 unit are these. It measures water in ppm from 0 to 500 parts per million, measures temperature from 0 to 55 degrees Celsius, and measures the amount of hydrogen in oil from 25 to 5,000 parts per million. The response time in this device is very low. It's less than 60 minutes. It has very low cross sensitivity, below 2%. The power consumption is just 60 watts, and the dimensions are quite suitable for operation in the field because it weighs less than 10 kilograms. That would be about 20 pounds. Next slide, please. The heart of that device is a sensor. That sensor is coated with thin nickel palladium film, and it reacts to the presence of hydrogen. The resistance of the film changes in the presence of hydrogen, and that number is converted into an electrical signal, then recorded and stored in that same sensor. And the change in electrical resistance is linearly related to the amount of hydrogen present in the sample of oil. Next slide, please. And this makes it a very compact and robust sensor that allows us to effectively and reliably monitor the content of hydrogen in the oil because it's resistant to both environmental elements and to any problems or interference that are related to the actual process of measurement. It has a self-calibration capability after all, so that's very easy to operate and handle. Next. One thing to mention about all of these TOR1 and TOR2 devices is that they're all designed for a quick operation, very simple to run the test. There are standard presets to do the test according to a certain standard, might be ASTM standard or any maybe European specification. So it's selectable with just one touch of the button, which is very handy. All right, so now that we've seen how to measure the amounts of hydrogen and moisture in the transformer, let's talk about how to get them out of our transformers. Next slide, please. So, okay, thermal vacuum process is a very common method, a very straightforward method of drying transformers due to the high efficiency and lack of any consumables in this process, no absorbents or anything like that. So the thermal vacuum process uses the physical characteristics of water just to extract it from the oil. We all know that water evaporates at its boiling temperature of 100 degrees Celsius, but that's just half of the story, because if we give the full answer, we should say that water boils at 100 degrees centigrade at 1 atmosphere of pressure. Now, the influence of pressure is very important for the boiling process, because when pressure increases, so does the boiling point, which indicates that they are directly proportional. When the pressure drops, the boiling temperature also decreases. Here in this graph up on top, you can see that If you'd climb the Rocky Mountains and be somewhere at maybe 10,000 feet, your boiling point of water will be around 90 degrees centigrade instead of instead of 100, excuse me. So, and this is very important because we want to get water from the oil, but we don't want to heat the oil because excessive temperature is dangerous and can damage the oil. This is why the process tool is exposed to reduced pressure vacuum, and this directly affects the water contained in the oil because water can now be extracted a lot more easily without damaging the oil. And the higher the vacuum we can achieve, the lower the pressure we got, the lower the temperature we can use to separate water and oil. And as we can see, this is it's just a physical process, no chemistry at all, no absorbance or anything like that. So it's a very straightforward and relatively simple process. However, it's important to make sure that oil remains under vacuum as long as possible to extend the degassing and drying, and of course to increase the surface area of the oil as much as possible. And there are various methods of doing this, but you want to achieve as high contact with the oil as possible, and this is done by spreading it very thin, like in a film. Next slide, please. So the use of the thermal vacuum processes also allows gases to be removed from the oil. And apparently, no other purification process can accomplish that. So it should be noted that thermal vacuum systems are effective for the extraction of water. So the thermal vacuum is much recommended because it affects quite a few of possible contaminants of the oil. The addition of hydrogen sensors to thermal vacuum oil purification equipment is actually a step forward in the quest for a more self-contained equipment that allows field diagnostics at the same time as the process runs to know how well we're doing and how efficient the process is and if anything needs to be changed or tweaked. And this eliminates the need to take samples all the way out to some external laboratory to determine if the desired results of the process have been achieved or not. We can know straight on site if we're doing a good job. We can go to the next slide. So, and this interesting curve here shows us how the processes differ depending on the subject of the process. So if we want to dehydrate and dry transformer paper, this is what happens. The water extraction rate is not linear. It runs just as shown in this plot here. The first stage from A to B, points A to B, that's the heating stage. And we have an increasing amount of water rather, that is being extracted from that paper. And when we go from point B to C, that plateau there, that stability stage, where the rate of moisture extraction is fairly constant. In this stage, we basically remove moisture from the outer layers of the paper. And the next stage is when the rate of moisture extraction dips quite low. And this is due to the capillaries in the paper inside the transformer. So there is water inside that paper in the inner layers of the windings, and that water must pass through the outer layers before it can be removed. And the slow rate of this passage of water causes this decline in the rate of water extraction. And so drying paper can take a long time. Therefore, it's a long process. So this means that to avoid that long downtime for transformer, it's very important to keep the moisture content controlled and to know what's going on and generally be on top of things here. So, and I guess this will be the conclusion of this presentation today. Again, I thank you all for visiting and for being here with us. Just to let you know that the next webinar is going to be on the 14th or the 15th of July. I believe it will be concerned with, well, anyway, again, yeah, just let me see. Okay, so somebody wrote in the chat the topic of the next webinar because I wasn't sure. I didn't want to mislead you or anything. So I'm looking forward to seeing you all on the in July. It's been a great time presenting to you. It's my honor. And once again, you can get a certificate of participants from any of the people here at Globe Core. And I hope to see you next time. Thank you very much.